In this video, we will learn about the homothetic functions. The definition is a function f of xy is said to be homothetic if it is a monotonic transformation of a homogeneous function. By this, what we mean? I am saying this f of xy, this function is homothetic if we can write it as the monotonic transformation. Let us say this f is, by monotonic transformation we mean if we can write it in this fashion as a composite function f of, let me write it here first, g of xy, then I will explain it. Okay, let me explain it. I am saying this function is homothetic if we can write it as a monotonic transformation of a homogeneous function. I am saying this g of x is a homogeneous function. I am saying this f of xy is homothetic function if we have two functions in this fashion. That is, one function is what we call strictly increasing. This capital F is a strictly increasing function, what we call the monotonic transformation. Okay, and we have another function which is homogeneous. Okay, let me repeat it again. I am saying this function is homothetic. This function is homothetic function if this function can be written as the monotonic transformation of a homogeneous function. G of xy is a homogeneous function and f is the monotonic transformation. Okay, what we call the strictly increasing function. And by this, what we mean, another property of the homothetic function is, and let me write it here, every homogeneous function, every homogeneous function is homothetic, is and what exactly is meant by homogeneous function? I have explained it number of times. I am saying that, let us say we have a function f of xy. Okay, I am saying this function f of xy is homogeneous. This function is homogeneous. Okay, if we increase all the inputs, all the variables by a factor lambda, and let me write it here, f of lambda x, lambda y. If I get the result in this fashion, that is lambda raised power n f of xy. Okay, I am saying f of x is homogeneous of degree n. Okay, if when we increase both x and y by a factor lambda, and if the output from this we get increased by a factor lambda raised power n, we say this function is homogeneous. Okay, I have explained this homogeneous in earlier videos, you can check. Otherwise, I will make a video on that very stuff also. The thing is, I am saying every homogeneous function is homothetic. Okay, now if we have a function and we are supposed to prove that whether a function is homothetic or not, first we need to check, that is, we need to prove a function is homogeneous. Okay, to prove a function is homothetic, we simply need to prove that it is homogeneous. And let me write it here, let us say we have a function f of xy is equal to xy. I am being told to prove whether this function is homothetic or not. Okay, to prove whether this is homothetic, okay, I simply need to prove that it is homogeneous. if it is homogeneous, then it is automatically homothetic. How do I prove that it is homogeneous? Let us say we increase both x and y by a factor lambda. Let me write it here in this fashion: f of lambda x lambda y. And what will happen here? So we will get x is being increased by a factor lambda, okay, and similarly y is also being increased by a factor lambda. Here we can see, we can write it here lambda x, or simply let me write it here. I don't have the space, so lambda into lambda is lambda square xy. And what I am getting here, I am getting lambda square f of xy, because xy is equal to f of x. So uh, f of lambda x lambda y. So this function is homogeneous of degree 2. Okay, so I am saying that f of xy is homogeneous of degree 2, that it then it implies f of xy is homothetic also. Okay, homothetic, because we know that every homogeneous function is homothetic. To prove a function is homothetic, we simply need to prove that it should be homogeneous. Since we got it as homogeneous, that means this function is homothetic. But another thing can happen here. Okay, sorry for my English, I'm not an English expert here. And let me rub this out now. Second thing is, and let me write it here, every homothetic function may or may not be homogeneous. And let me write it here, every homothetic function may or may not be homogeneous. What I am saying by this, so every homogeneous function is automatically homothetic, but every homothetic function may or may not be homogeneous. Now let's take an example. Let us say we have a function f of x comma y is equal to e to the power x plus y. Okay, first we need to see whether it is homogeneous or not. If it is homogeneous, then we stop and we conclude that okay, this is also homothetic. Okay, let us see whether it is homogeneous or not. For homogeneity, what we need to do, we increase both variables x and y by a factor lambda. Let us say f of lambda x is being increased by a factor lambda, and y is also being increased by the same factor lambda. And what will happen here? So in place of x we have lambda x, and in place of y we have lambda y. Here you can see it is equal to e to the power lambda x plus y. Is it homogeneous? Definitely, absolutely not. Okay, why? Because this lambda should have been here. Since the lambda is in the exponent, we can say that okay, when we increased both inputs by a factor lambda, this is uncertain what has happened here, because if lambda was at this point, we could have concluded that okay, our this function is also increased by a factor lambda. But since lambda is at the exponent, we can say that this function is not homogeneous. Okay, one thing. Okay, so what is the problem if it is not homogeneous? Can this function still be a homothetic function? Yes, we can see. We have to check that very thing. Okay, for that, let us suppose, and let me write it here, let this x plus y or let me write it in this fashion. Let us say g of x comma y is equal to x plus y. Okay, so in place of x plus y, I am writing it as a function of g of xy. Then can I write this function as f of x comma y is equal to e to the power g of xy? Yes, I can write it in this fashion. So now we are involved all this with composite functions here. So I have written this function in this fashion, that is f of g of xy. Okay, so simple thing is, if a function is homogeneous, it is automatically homothetic. But if it is not the case, then we need to use this very stuff, that we should get um, you know it as the monotonic transformation of a homogeneous function. Okay, now next thing is, we need to prove that this capital F is monotonic transformation, or this capital F is strictly increasing function. Okay, so how do we and here we can see by simply, if I write, and let me rewrite it, we got it as f of g of xy is equal to e to the power g of xy. Okay, now is this function strictly increasing? That means df upon dg. Okay, is it strictly increasing? Yes, it is greater than 0, because we know that the exponential function is always positive. So first thing is, we should get a strictly increasing function, that we got here. Second thing is this g of xy homogeneous? And let us see, since g of xy is equal to x plus y, is it homogeneous? Let us see. Increase x and y by some scalar, lambda x comma lambda y, which is equal to lambda x plus lambda y. Here we get lambda common, and we write x plus y, which is equal to lambda g of xy. Okay, we got both the things here. That means this f is monotonic transform, or it is strictly increasing. Okay, clear. Second thing is that this monotonic transformation is of a homogeneous function. Okay, so g of x is homogeneous function. Then we conclude here that this function is homothetic. Okay, and let me take another example to explain this point again. Okay, so let me first explain this. So I am saying that f of xy is equal to e to the power x plus y is homothetic. Okay, but it is not homogeneous. So for homotheticity, we need to prove two things. That is, first, this function, this capital F, should be monotonic transform, or it should be strictly increasing function. Strictly increasing function means the derivative of this function with respect to this homogeneous function should be greater than 0. And second thing is that this g of xy should be homogeneous. Okay, if both the conditions are met, then I can say that this function is homothetic. Okay, let me take another example here. Okay, let us take the same example, rather a different one. Let us say we have f of x comma y is equal to e to the power xy. Okay, is it homothetic? Sorry, is it homogeneous? Let us see here. So f of lambda x comma lambda y is equal to e to the power lambda x lambda y. We get here e to the power lambda square xy. So this is not homogeneous. Okay, now we still need to prove, we can still prove that it is homothetic. So for this, what will we do? We should get two things. We should satisfy two things. That means that f should be strictly increasing function, increasing, and another function g, okay, g should be homogeneous. Okay, let us see here. So we have this thing, and let us say let g of xy is equal to xy. Okay, then can I write this function f of xy, f of xy is equal to e to the power g of xy. I can write it in this fashion, okay, e to the power, because xy is a function of g of xy. Okay, now is this function strictly increasing? Okay, or we can write it in this fashion, f of g of xy. Is this f of g of xy monotonic transformation? Is it strictly increasing? Yes. Again, df upon dg, it is greater than 0 because exponential function is strictly increasing. So this condition is met. And second thing, we need to prove that this g of xy is homogeneous, and we can prove it again. G of xy comma xy is equal to xy, and if we increase both x and y by a factor lambda, then what will happen here? So we get lambda x times lambda y, which gives us lambda square xy, which is equal to lambda square g of xy. Okay, so here we got both the things. First thing is that we got a strictly increasing function, and g of xy is homogeneous. Then we can conclude that this function is homothetic function. Okay, so if a function is not homogeneous, it can still be a homothetic function. Okay, but every homogeneous function is homothetic. I hope I make myself clear in this video. See you in next video.